So, in this lecture 4, I will be discussing a bit of interacting systems. Before that, let me recapitulate at least some aspects of whatever we did in the third lecture. So, this is our lecture number 4. We shall start by recalling what we talked about: specific heat capacity, we introduced the notion of CV, specific heat measured at a constant volume, CP, specific heat measured at a constant pressure, and CP minus CV, CP minus CV is equal to R for an ideal gas. This I did not prove, but we accepted this form. 3 situations we talked about. Firstly, what is most important is equipartition. Of energy. Okay. I said each degrees of freedom contributes half kT to the energy. Okay. This is called equipartition theorem. What is important? Energy is equal to P square over 2m. Okay. So, this quadratic form of energy is very important in having this form of half kT. So, now we did it for monoatomic gases. For monoatomic gases, we know there is only translational degrees of freedom. So, n monoatomic gas molecules will contribute an energy 3 by 2 n kBT. Okay? 3 because it is 3 dimension, 3 components of momenta, and each giving me half kT. N is the total number of molecules. So, I found out CV should be equal to 3 by 2 R and CP is equal to 5 by 2 R. Okay? So, this is the simplest situation where we can have only translational degrees of freedom. If I go to diatomic situation, diatomic molecules, we should be careful, because what I did in the last class is a rigid approximation. I will take you slightly beyond that and tell you vibrational modes also. So, I can have translational, plus rotational, and vibrational. In the last lecture, I focused on these 2 parts for diatomic molecules, translational and rotational, assuming a rigid diatomic molecules. Okay. So, translational degrees of freedoms are very simple. They will give me 3 by 2 n kBT because it is 3 dimension. But if you think of rotation and if you assume that there is a dumbbell like structure, this length being fixed, this is the rigid approximation, then you can have rotational 2 rotation axes. One you can think of lying on the board this is the center of mass, let us say. One is lying on the board, other is coming out of the board or going into the board. And we know rotational kinetic energy corresponding to these two modes, they will be of the form half I omega square. Two of these terms will come. Moment of inertia, let us write it of this form corresponding to axis 1 we have drawn, and there will be another corresponding to axis 2. Once again this quadratic form is very important, with angular velocity will give me half kt. So, I will be getting another half kt into 2 because of 2 rotational degrees of freedom plus kBt. This I did in the last class. This gives me 5 by 2, and you can immediately find out what is Cp if I give you this form 5 by 2 kBt. If I have n molecules, I should be having an n here. So, Cv will be given by 5 by 2 R. But that is not all. There could be vibrational modes. Now, this vibrational mode I wrote as F in the last class, but one has to be careful. Okay? I said F by 2. F by 2 you can add, but one has to be careful here. Why it should be careful? A vibrational mode corresponds to a situation like a simple harmonic oscillator. In a simple harmonic oscillator, you know that there is a Q and there is a P, which I discussed in the last class. If we have E of the form P square over 2m plus half kx square, I have 2 degrees of freedom, because I told you that my style of counting degrees of freedom will be including P as one, x as another. So, it will give me from equipartition at temperature T, if I have a system of harmonic oscillator, okay, in one dimension, say at a temperature T, I will be having energy is equal to En kVt. So, each vibrational mode which I wrote F in the last class, I wrote F by 2, assuming that F is 2 for each vibrational mode. To be precise, one can write Cv is equal to 3 by 2 R some F prime. What is difference between F? F has 2, both Q and P. Okay? F prime, if I add with this, so I will get Cv is equal to, let me correct this part of it, 5 by 2 I was getting, Cv is equal to 5 by 2 plus F prime kVt. Okay? F prime, each vibrational mode has one coordinate, one momenta, each contributing half kt. Okay? So, if you write F prime, it is of the order of 1 kt, or you can write it simply, I write it as F. Okay? As long as you remember, F has both kinetic and potential degrees of freedom, each contributing half kt. This is what I wanted to clarify. So, remember, whenever there is a vibrational mode, there is a F, and that F is actually having a contribution from kinetic energy and having a contribution from potential energy. So, it will be F kt. Okay? F counts both x and p here. So, if you have one vibrational mode, so you will be having one harmonic oscillator, one p gives me half kt and other half kt comes from this x component. Okay? Now, generalizing to polyatomic molecules, polyatomic, which I did also in the last class. Polyatomic, there will be a three factor which will come because of the rigid body approximation, and with this 3 you should have this F okay, and here I should correct myself, this should be n, this should be 5 by 2 3 plus f into r. Okay. This is specific heat capacity for the polyatomic molecules. So, idea is count appropriately the degrees of freedom, and vibrational mode, if I mean f, each f one translation, one potential, giving me a kT. Okay. Having said this, now I will introduce mean free path in far more details. Okay. I introduce the notion of mean free path, but I will do it in a more detailed manner in the coming few minutes. Okay. Okay. Let us define what is mean free path. I have been so far assuming that my gas molecules, if not otherwise mentioned, these gas molecules are monoatomic molecules, and I am assuming that they suffer no other collision except for the elastic collisions with the wall. That is how I arrived at the expression P average pressure, P is 1/3 mnc square. But this is too idealized situation which is valid only in the dilute limit. So, there is a mean free path, and the mean free path is the mean free path which I also defined in the last class is the average distance traversed by a gas molecule between two successive collisions. This is what I defined as mean free path. Okay? Important is average. I told you everything we derive in this set of kinetic theory lectures are average in average spheres. So, I define again the average speed of a molecule let me call it V bar. Okay. Now, what is the distance travelled by this molecule? In time delta t, that is V bar into delta t. Okay? And let us now assume that this molecule has a diameter d. Identical molecules I am dealing with. In a sense, I can assume all the molecules have a diameter d. Now, this is the deviation from ideal gas situation, where we initially we made the approximation that molecules are point particles in comparison to the intermolecular separation. But now, I am making an approximation that molecules are hard spheres. This is very important. Molecules are hard spheres of diameter d. Now, how do I calculate mean free path from these approximation? So, let us draw a cylinder. Okay. This is V delta T, that is the average distance traversed by the molecule over a time delta t. And now let us assume that this area is pi d square. Okay. So, this area is pi d square, this radius is d, but I have already defined molecular diameter is d. So, molecular radius will be d by 2. Okay. So, I am constructing a cylinder which has this length, height v delta t, diameter d, where molecular diameter is here, which is I have defined d by 2. If I take this only this area and draw it, this is my d and this is my d by 2. Okay. Now, we will make an assumption. Assume all other molecules are static. Okay. This is an approximation, but basic result does not change, alter much if I do not make this approximation. Now, you can see very nice situation. What I assumed, molecules are hard sphere, okay, of diameter d. Now, any molecule, if I can think of, all the molecules are static, my target molecule which I have talked about here is moving, and this covers this cylinder, this inside cylinder over a time delta t. Now, you see, if any molecule collides with this, its center must lie within this cylinder. Okay? If its center lies inside, or optimally center lies on this cylinder, there will be a collision. Okay? That tells me the number of collisions that the molecule will have. Which molecule? The target molecule, that is moving. Other molecules are static. Whenever any one centers lie here or inside, there will be a collision. So, how do we know the number of collisions? Total number of collisions, in that case I can easily calculate total number of collisions. If I assume n is the number density, this is the cylinder area, pi d square V average delta t. This is the total number of collisions that it will have. Again, I am making an approximation here, I am assuming homogeneity, that density is same everywhere. It does not matter where this target molecule is moving. That means, I am assuming I am far away from the wall. Okay? So, if that be the case, now I can find out the rate of collision, how many collisions it will suffer per unit time. So, this is the number of collisions over a time delta t, and then time between two successive collisions is n pi d square V average. What is the average distance between two successive collisions? That I can easily calculate. So, average distance which I defined as mean free path is V into tau, okay, V average into tau, that takes care of V here, and I get n pi d square. you can easily check that dimensionally it is actually dimension of length, okay, because this has 1 by L cube, this is L square. So, you get L. So, this is typical mean free path, which as it takes into consideration of the fact that dilute gas, but if it is too dilute, then you see N is in the denominator. So, this number of mean free path becomes very, very high. So, for practical purposes, that these length is very, very large, and one can, for mathematical purposes, one can assume there is no collision inside the container. But for realistic situations, there is a mean free path given in terms of N and D. But that is not the end of the story. I made an approximation that all other molecules are static, which is not true obviously. We know we do not have any specialized molecule or specific molecule that is moving. All the molecules are moving. So, one should actually have here the V relative, which is relative velocity between two molecules, okay. But that does not alter this result much. All that you can have a number, and more sophisticated calculations will give this number probably of the order of root 2. But essentially the functional form or the mathematical form we have found out holds true. So, this completes more or less all I wanted to say about ideal gases. Now, it is time to go beyond ideal gases and do little bit of interacting systems. Again I recall why interacting systems are important. Interacting systems are important because in nature we always see phase transitions, okay. We boil water even to make a cup of tea, we see ice in our refrigerators. These phase transitions are never possible, as I also emphasized in the last class, are never possible without interaction. And what type of interaction? Okay. Let us take very, very simplistic interaction. I said in deriving the mean free path expression, I assumed that they are hard sphere molecules. They cannot penetrate into each other. This is a good approximation to some limit, but in fact molecules are soft. So, they can penetrate in some sense, but let us not go into this. So, first I will consider interaction which is hard sphere interaction, okay. Hard sphere interaction. That means they cannot penetrate into each other. This is a strong repulsion. Okay. And then there is a weak attractive interaction, but very short range. Okay. So, very short range weak attractive interaction when the molecules are away from each other. If they are close by, there would be a hardcore repulsion, okay, which is very strong, which is mostly dominating in the short ranges. They are far away, there is a weak attractive interaction which is very, very small in magnitude and short ranged. Okay. This has origin from electrostatics, but I will not explain why and how. But since you know potential energy, I can draw a curve of potential energy, and as a function of r, let us say, you see what happens, there is a strong repulsive potential up to a distance. This is the nearest distance molecule can approach, and then there will be a weak attractive potential. I am simplifying it to this very simple form. Actual form, if you are interested, you can find out. Its name after two famous scientists. It is called Lennard-Jones potential. But this is the simplest form one can think of, that there is a strong repulsion potential as a function of R. You see there is a strong repulsive force, there is a weak attractive force, and this, when taken into consideration, you have already seen that I have a mean free path. Secondly, I will have change in my ideal gas equation of state. Okay, this was my equation of state. Boyle's law, Charles' law, everything we found out from here, but what we will get? Simplest correction to ideal gas scenario is van der Waals equation of state. Okay. I will spend just half an hour on this van der Waals equation of state. Let me write it in this form: P plus A V square V minus B is equal to RT. I am assuming 1 mole of van der Waals gas, let me call it a real gas. So, you see the two correction, one correction arising due to this. So, a correction to pressure arising due to this attractive force. In the beginning, we said that our ideal gas molecules will be molecules which do not have any other interaction except for elastic collisions. I make a departure from that. I said there is an attractive force, very weak, short ranged. This attractive force, average attractive force, leads to a correction to pressure. Okay? And second thing, a correction to volume. You can already guess why this correction to the volume. Okay? Correction to the volume is coming because of the second issue. I assumed molecules to be point particles. We have already seen in the beginning of this lecture, they should be taken as Hertz sphere. That is also an approximation, but it is a better approximation than point particles. So, there will be a correction. Why this correction? The entire volume of the container is no longer available to a molecule. Some volume is excluded. V measures the volume that has been excluded. Now, clean this part of the board, but what you have to bear in mind that there is a correction to pressure arising due to the attractive weak force, and here there is total correction to the volume which takes care of total volume of the container that is excluded. It must be excluded because in van der Waals approximation we are considering molecules to be Hertz spheres. Now, let us try to do this in the following way. First, let us assume identical particles. Many times I have repeated, they are Hertz spheres. These Hertz spheres are of diameter d. Okay? Now, let us take two of them. Consider one of them which is static, or more scientific way or more physical way of saying this, I am moving in the frame of these molecules, I am moving with this molecule, so that to me it is static. Okay. So, this is one having diameter d, this is diameter d. Once I have of this form, now I draw a bigger sphere as I did while I was deriving the mean free path. Sphere, a concentric sphere which has a diameter 2d or has a radius d. Okay. Now, again recall the argument I gave while introducing mean free path. What is that? That's if I have any other molecule whose center comes here, then there it will be a hardcore repulsion. Okay. There will be just deflected, there will be a collision because molecules cannot penetrate into each other, they are hard spheres. So, if that be the case, then I can say each molecule has an excluded volume. What does it mean? This molecule moves, but hard sphere condition also gives me a sphere which has a radius d. This volume is entire volume excluded, okay, for other molecules. I am considering a second molecule, this volume will be excluded for the second molecule. Okay. So, every molecule then carries with itself a volume that is excluded. And what is the volume of this sphere? Okay. Volume of this sphere, okay, will simply be 4/3 pi, but here the sphere, this bigger sphere has a radius which is double the radius of the molecule itself. Okay. So, I can write it as d q. Okay. This is the volume that it excludes. I again repeat the argument, volume excluded. I repeat the argument, that is the sphere, okay, center of any other molecule I consider can lie maximally here. It cannot come closer because in that case it will have to penetrate the first molecule here. So, this is the volume of excluded by this molecule I am considering. So, I can write it in the following form, which is like this: 8/4 pi d by 2 q. Well, immediately I know what is 4/3 pi d by 2 cube. This is the volume of my molecule. If you remember, initially I started by saying that B is proportional to the volume of a molecule. Is that clear? If that is clear, you see it is 8 times V molecule. It is not the velocity, it is rather the volume of a molecule, assuming the molecule to be a hard sphere of diameter d. Now, I am taking two molecules into consideration. I am asking the question, one molecule is there and how much volume it excludes for the other molecule. So, 2 in the picture. So, on an average, this is van der Waals original way of argument. Okay. I can say, if I considering 2 molecules, average excluded volume will be half of this quantity 8 times volume of the molecule, which tells me that on an average the quantity B will be proportional to 4 times the volume of a molecule. So, B, I would rather write B will be proportional to 4 times V molecule. Of course, proportionality constant will have number of molecules in the container. More molecules I have, more will be excluded volume, more and more volume will be excluded, okay, and we will have serious correction to this term. So, this somehow gives you a feeling, I am again telling I am not deriving anything, okay, phenomenological argument why there should be a V minus B term. Next comes the question, how do you get this A by V square term? Okay. A by V square term can be appreciated recalling there is a weak attractive force, but this weak attractive force is very short ranged. So, we can assume whenever my molecule, any molecule I target is moving within the container, okay. Let us assume this room as a container. So, whenever molecules are moving inside the this container, so I know this weak force can be neglected, but two approximation which ideal gas makes. One is there is no interaction, fine, let me drop it, but when it goes to the wall, some molecules are in the wall and some molecules are inside. Consider one molecule that hits the wall. What will happen to other molecules? They have an attractive force, they will collectively pull this fellow. The fellow molecule that is hitting the wall, that is at the edge. You can think in the following way. If I have a molecule inside the container, it will have an attractive force of all the other molecules surrounding it. Roughly speaking, I can say that net average force acting on it is 0. But when it is on the wall, okay, then other molecules which are inside will collectively pull it inside, okay, and this will change the pressure. Pressure, when we derived, we assumed no interaction from other molecules, but if other molecules attract them, molecules on the wall I mean, then there will be a net attractive force, okay, that is going to reduce the pressure. There could be one more situation which I had never considered in my derivation, okay, that is the wall. Wall, I always assumed the wall to be a fixed body and it has no interaction with the molecules which are going and hitting them, okay. This is also a very idealized situation. We all know there is adhesion, there are phenomena in which liquid molecules interact with the wall. So, two approximations, there is one attractive force inside the container, I can forget about it, but whenever a molecule hits the wall, it must feel a net attractive force inside due to the other molecules of the container, and wall also should have a repulsive force, okay. These two taken together must give a correction to the pressure I have been talking about. So, two contributions that I will take into consideration to interpret or to appreciate the origin of the term A by V square. Okay? So, one weak attractive force to repulsion from the wall. Okay, repulsive force. Now, here I bring in the concept of homogeneity. Okay. Homogeneity will tell me that what is this interaction are proportional to. Okay. You can say at any instant of time, number of molecules that hit the wall will be proportional to the density that we have already seen. So, first number of molecules at any instant hitting the wall will be proportional to the density n over V. Okay. Secondly, how many molecules are attracting it inside? Okay. Number of molecules on the wall is n by V, and whatever is attracting them will be also proportional to n. So, two things: number of molecules at any instant hitting the wall would be proportional to small n, which is density, and again the number of molecules which are pulling them should also be proportional to n. So, correction, if I write my pressure equation, so this pressure will be proportional to n square. Okay? Just n on the wall, n on this. This correction is incorporated in the form n is, I remind you, capital N over V. More sophisticated language, I can call it a density-density interaction. Okay? So, this is proportional to n square or 1 by V square. Now, taking this two into consideration, my pressure form will be RT V minus P. I tried to emphasize how does B come, and there will be a correction coming because of this interaction I talked about, number of molecules hitting their wall and number of molecules which are pulling them, both being proportional to small n or 1 over V. I will have a correction of the form A over V square, and then immediately putting thing together I will get A V square V minus P is equal to RT. So, this gives me the van der Waals equation for 1 mole of real gas. Okay? Now, having said this, in last 10 minutes of my last lecture on kinetic theory, I will try to tell you why van der Waals equation is so important. Okay? We always talk about liquid gas transition. Okay? What is a liquid gas transition? You have a liquid and you heat it up, okay, and you get a gaseous state. Kinetic theory tells us has to happen because kinetic energy of the molecules, average kinetic energy of the molecules is proportional to the temperature. Okay? If you increase the temperature, kinetic energy will be very, very high and it will go to a gaseous state, freely moving. Okay? Now, also there is a liquid gas transition, and you may have noted sometimes we call gas, sometimes we call vapor. The ideal gas equation will never be able to tell me about this transition or about the liquid and vapor, what is their difference. Van der Waals equation tells you that, and though it is a very phenomenological derivation, almost guessing the corrections, okay, still experimental plots, if you look for, if you just Google van der Waals equation experimental plots, you will see similar plots were experimentally observed more than 100 years back. So, what I am going to plot is called isotherms. Okay. Isotherms, these terms you will see many times, these isothermal, adiabatic in thermodynamics part of this set of lectures. What is an isotherm? You keep temperature constant, this is very important. Okay. You keep temperature T constant, okay, and then plot pressure as a function of volume. Okay. These are called isotherms. You plot it for different constant temperatures. Okay. Now, let me plot van der Waals isotherms and let us see how can it talk about liquid gas transition, okay, and secondly how does it talk about the critical temperature which I am going to tell you now. So, first let me plot pressure as a function of volume. This is my first curve, okay, for a temperature T1, this is for a temperature let us say T2, pressure as a function of volume, this is T1, T2, let me plot some particular temperature, I am calling it Tc or the critical temperature, and above this, this is my curve. Now see, let me make this curve slightly more realistic. You see there is a region which is almost horizontal. This region is called the coexistence region, okay, and I demarcate by this region by this dotted curve, okay, and this region is coexistence of liquid and vapor. Okay. So, you increase the temperature, okay, you go from the one phase to the other, temperature is increasing in this direction, this is T greater than Tc. So, T1, T2 is higher than T1, Tc is higher than T2, and what you see this dotted region tells you the coexistence region shrinks to a point at that critical temperature. So, what is the importance of critical temperature? Firstly, if you change pressure, okay, if you change the pressure, this is your high pressure, low volume, this is low pressure, high volume region. So, liquid and gas, they coexist here in this region, okay. But as you increase the temperature, this coexistence region shrinks to a point, and for temperature greater than the critical temperature, there is no such coexistence region, okay. This is the first meaning of the critical temperature. So, if you change pressure, there is a coexistence region between liquid and gas, okay, or rather liquid and vapor. Why I change the terminology? You will soon see. Because below the critical temperature Tc, you can change pressure and go from one phase to the other, okay. This is second implication or related implication. I will call a gas a vapor below the critical temperature. Above the critical temperature, what would happen? no amount of pressure, can liquefy a gas. This is the implication of so called critical temperature. If you want to plot PT diagram, P as a function of T, this is also very useful, okay, keeping volume fixed, you will see that this PT diagram ends at the critical point, okay. This is your gas and they coexist up to critical temperature, and beyond that there is no coexistence. So, van der Waals equation which I explained for you leads us to following things. It explains liquid gas transition which we observe in nature. This liquid gas transition can be achieved by changing temperature, okay, we will boil water all the time, or by application of pressure, okay. But if I am sufficiently high in temperature, which is the critical temperature, okay, we cannot liquefy a gas by application of any amount of pressure. If I am below Tc, critical temperature, there will be always a coexistence region in which vapor and liquid will coexist. Either it is entirely liquid phase or it is gas phase or it will coexist, okay. So, this is the summary, okay, of implication of van der Waals equation. So, I corrected ideal gas equation to the van der Waals equation, taking into consideration finite size of the molecules that give a correction term to the volume, weak attractive force between the molecules which was otherwise completely neglected, and that resulted in some interaction which is proportional to the density of the molecules, and hence there was a correction to the pressure which was not there in the ideal gas case. Fine, that leads us phenomenologically to the van der Waals equation which I have written here for 1 mole of real gas. If I plot van der Waals isotherms, this tells us nicely that there could be phase transition either by changing temperature or changing pressure, but there is a critical temperature above which no amount of pressure can liquefy a gas if I am at temperature T greater than Tc. For T less than Tc, I can achieve that through a coexistence region in which liquid and vapor coexist. For T less than Tc, I will call it a vapor. T greater than Tc, it is a gas. Kinetic energy dominates, pressure cannot liquefy it. With this, I will end my set of lectures on kinetic theory, and next set of lectures will start discussions of thermodynamics. Thank you for today's class.